Welcome back, and we're continuing our study on probability distributions. And as promised, today we're going to talk about discrete distributions, more specifically binomial probability distributions. And you're either going to like this topic or not like this topic. Binomial distributions. So there are many probability experiments for which the result of each trial can be reduced to two outcomes, either success or failure. And these are called binomial experiments, bi meaning two. A binomial experiment is one that satisfies the following conditions. The experiment is repeated for a fixed number of trials where each trial is independent of the other trials. There are only two possible outcomes, like I said, success or failure. The probability of success is the same for each trial, and we have a formula for you. You ready for this? There we go. Yeah, I know. It looks a little bit freaky, but it's not too bad. Let me break it down for you. Okay, so here's our formula, and we're going to break down what each of the letters means. So N, that's the number of times that the trial is repeated. X is the random variable, represents the count of the number of successful trials. P is the probability of success in a single trial. And Q is the probability of failure in a single trial. So sometimes it's easier just to jump into an example to see how it works. So here's our first example. ACL reconstruction surgery has an 85% chance of success. The surgery is performed on 3 patients, and we're going to find the probability of the knee surgery being successful on exactly 2 patients. So I always find it helpful to just list each of the variables I need. So P, that's the probability of success. We have an 85% chance. Q is going to be the complement of that. So 1 minus 0.85. 0.15 is the probability of failure. N, we have 3 patients. And X, we're curious about the probability of the surgery being successful on exactly 2 of them. So if we put all those numbers into the formula, we have the probability of X equals 3 combination 2 times 0.85 squared times 0.15 to the 3 minus 2. Okay, let's simplify that a little bit. 3 combination 2 is 3, and then we've got 0.85 squared, 0.15 just to the 1 power. And if you plug all that into your calculator, you get the probability of 32.5%. It still seems a little bit overwhelming. I understand that. So here's what you do, is you pull out your nifty graphing calculator, and your graphing calculator will do it all for you. So you hit second vars, which is you're going into the distribution part of your calculator, and it brings up this menu, and you're going to scroll down until you find Binomial PDF, and you want to hit that. And your calculator might bring up this menu where you just plug in the number of trials, the probability of success, and your random variable. Some calculators might just bring up this on the screen, Binomial PDF, and you need to type in N, P, X, and then hit enter. It does all the calculations for you. Let's try another example. According to Forbes.com, 66% of students graduate from a public college with student loan debt. If you randomly selected 400 graduates, what is the probability that exactly 265 of them will have student loan debt? So P in this case is 0.66. Our Q, the complement of that, is 0.34. N is 400, and we're curious about 265 of them. So again, we can just use the binomial PDF function of our calculator, plug all that in with 400, 0.66, and 265, and we find that the probability that exactly 265 of them will have student loan debt is about 4.2%. Let's try another example. According to the U.S. Department of Health and Human Services, only 29% of adults meet the guidelines for aerobic and strength training activities. If you randomly select 50 adults, what's the probability that exactly 12 will meet the guidelines? So again, we need to find our variables. P is 0.29. Q is the complement of that, 0.71. N is 50. X is 12. Plug all that into your calculator, and you've got about a 9.6% chance that exactly 12 of the adults that you pick of the 50 will meet the U.S. Department of Health and Human Services guidelines for aerobic and strength training activities. Okay, let's go a little bit further in this. So according to the Pew Research Center, about 6 in 10 adults, 62% specifically, say that it's very or somewhat acceptable for professional athletes to speak out publicly about political issues. If 4 adults are chosen at random and asked if it's very or somewhat acceptable for professional athletes to speak out about political issues, find the following probabilities to the nearest thousandth. So we want to know if exactly 2 of them respond yes, the probability that at least 2 of them respond yes, and the probability that fewer than 2 of them respond yes. So first we're going to create a probability distribution. So we'll get a table ready, and we've got the random variables 0, 1, 2, 3, and 4 for our 4 adults. And for each of them, we'll have the probability of success being 0.62, and of course we have 4 adults. So we're going to use the binomial PDF function of our calculator and calculate the probability of each of these. So the first one, we're going to calculate the probability of 0 adults saying that it's acceptable is 0.021. The probability of 1 adult saying it's acceptable is 0.136, and then 2, 3, and 4. So each of those you're plugging into your calculator. Now we can find the probability that exactly 2 of them responded yes is right here, 0.333. What about the probability that at least 2 of them said yes? So at least 2 means it's 2, 3, or 4. So we have to expand that a little bit, and we can just add all those probabilities together to get 84.3%. What about the probability that fewer than 2 of them respond yes? So that would be like x equals 0 or x equals 1. We add those 2 probabilities together and get about 15.7%. Let's do another example. A new Pew Research Center analysis of surveys conducted between October 2019 and June 2020 finds that 18% of adults rely on social media for news. You randomly select 6 adults and ask each if they rely on social media for news. Construct a probability distribution to the nearest thousandth and graph the distribution. So first thing we need to do is create the probability distribution. So the probability of success in this case is 0.18, and our n is 6 because we're randomly selecting 6 adults. So again, we're going to use the binomial PDF function of your calculator, and for each of the random variables, 0, 1, 2, 3, 4, 5, and 6, you'll find the probability. So there we have a probability distribution. Feel free to pause the video if you need to catch up. Once we have our probability distribution, we can make a lovely graph to get a visual overview of how these probabilities work out. Now remember, like a picture is worth 1,000 words, a graph is worth 1,000 numbers. With any probability distribution, we can find the mean, the variance, and the standard deviation, and I'll show you how. In Colorado Springs, Colorado, we have about 67% of the days of the year that are sunny. That's awesome. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. If an unusual value is 2 standard deviations above or below the mean, what would an unusual June look like in terms of weather? All right, let's get our variables going here. So we have an n of 30 because there are 30 days in June. Probability of a sunny day is 67%. The complement of that is 33%. Now, to find the mean, variance, and standard deviation, we have some formulas. To find the mean, you just multiply n times p together. So in this case, 30 times 0.67, which is about 20.1. To find the variance, you multiply n times p times q. So 30 times 0.67 times 0.33, which is 6.633. And to find the standard deviation, well, you just have to take the square root of that, 2.575. Now the question was, what's an unusual June? So we take the mean, okay, and we're going to add and subtract two standard deviations. So an unusual June would be anything below about 15 days of sunshine or anything above 25 days of sunshine. So that's probability distributions, specifically binomial distributions, and I hope you liked the lecture. Thanks for being here.